All right, this might be a little bit of a sensitive question, but how much time do you spend on your phone per day? Like, is it a lot? Is it a little? How does it compare to other college students? How does it fit into the broader story of screen time for the overall population of college students in the country? Let's say that this was something that we wanted to research and dive into a little bit deeper and understand a little bit better. One thing that we might start with is just by answering the question of what even is the average screen time of all college students? The tricky thing with that though is how could we actually find that average in practice? Well, ideally we'd just be able to ask every single college student in the whole country what their screen time is, and then as we've talked about in previous videos, we would add all of those numbers up, we would divide by how many there are, and that's what would give us the average. But of course,
ain't nobody got time for that.
So instead, we can take a sample. Okay, so suppose I survey 30 students, record their daily screen time, and calculate the average amongst those 30. And let's say we compute that as 5.8 hours. This number, 5.8 hours per day, represents the mean of that sample. But is that mean, that average screen time, the same for all college students? It might be close, it's probably close, but almost certainly not exactly. And this is one of the fundamental ideas of statistics. Our question is centered around the whole population. We want to know the average screen time of every college student in the country. But typically, we're only able to access a small sample. We only have the capacity to observe, say, 30 college students at a time. And so we take a sample and compute a sample mean. And that sample mean can make a good guess for the population mean, but it's not exactly the same. And if we surveyed maybe a different group of 30 students, they'd likely have a slightly different average, a slightly different estimation for the mean of all college students, the mean for the full population. So we're not going to stop here and say that average of 5.8 is the average overall. That's just an estimation. But we need a way to express how good of an estimation it is. Like, how much uncertainty is there behind that number? How much uncertainty is there around that guess? Well, think about it like this. Imagine making a giant list of all of the college students in the country and repeating this simple process. Randomly select 30 of them as your sample, compute the average screen time for those 30, take all of those 30, put them back onto the list, and then just repeat that process again and again. Each dot here represents a different sample mean, a different mean computed from one of those groups of 30. Notice first that they're not all the same, but also they tend to cluster around a central value. That spread happens because of the sampling variability, randomness from who happened to be selected in that sample. And because this randomness is unavoidable, we need a way to account for it. A confidence interval is how we deal with this. Essentially, a confidence interval is a set of plausible values for the population mean based on the estimation we're making from our sample. As we saw from the chart, where we imagined repeatedly sampling different sets of 30 students, the sample means span a whole range of values. What we can do instead of just reporting a single number is report a range of values as our estimate. That range is what we'll call a confidence interval. For example, we might estimate that the population mean for daily screen time lies somewhere between, say, 3.8 and 7.8 hours. Looking at our sample means, that's a pretty wide range. The vast majority of sample means fall between these two values, so this is probably a safe enough statement to make. In other words, we can be fairly confident that the true mean screen time of all college students in the country falls somewhere in that broad range. We could, though, choose to make a much narrower estimate and say that the population mean lies somewhere between maybe 5.6 and 6.0. Some sample means do still fall between those values, but noticeably fewer than before. This gives us a much more precise range, but because many more sample means fall outside of it, we can't be as certain that we actually captured the true population mean. And this highlights a fundamental trade-off. If we make our interval very wide, we can be pretty confident that it captures the true mean. But the statement may not be very informative. For instance, I could even say I am 100% confident that the average daily screen time for college students falls somewhere between the range of 0 hours to 24 hours per day. That's almost certainly correct, but also not very useful. On the other hand, if I try to be extremely precise, maybe something like between 5.75 hours and 5.85 hours, that's a very small window. Because it's so narrow, I can't be nearly as confident that the actual mean falls within that range. So we have to balance precision and confidence. The more precise I want my claim to be, the less confident we can be in it. And the more confident we want to be, the less precise of a claim we can make. There's no one right way to approach this, but it's a decision that we have to make deliberately and thoughtfully when reporting these kinds of results. Now, this is where what we call a confidence level can come in. We can make a decision about how confident we want to be in our interval. For example, we might say something like 90% confident, or 95% confident, or 99% confident. And all of these are valid choices depending on the situation. Different fields tend to adopt different standards. For example, in many social science settings, researchers will often use 95% confidence, meaning they're willing to be wrong about 1 out of every 20 times in the long run. In maybe a medical or safety related research setting though, 99% confidence is probably a little bit more common because the cost of being wrong is also much higher. So it's something that will vary from context to context. Now, it's important to be very clear about what something like 95% confidence actually means and what it doesn't. First, when we say we are 95% confident, what we are not saying is there is a 95% chance that the true population mean is in the interval. Once the interval is created, the true mean either is there or it isn't. There's no probability involved anymore. Instead, when we say 95% confidence, that 95% refers to the long-run behavior of the method, of the process. Let's go back to our repeated sampling process. If we were to, number 1, take a random sample, 2, build a confidence interval around it, 3, put the data back, and then 4, repeat that process over and over and over again, then about 95% of those intervals that we build would contain the true mean. And of course, about 5% of them would miss that true mean. And that's what we mean when we say a 95% confidence interval. 95% of the intervals that would come about by repeatedly sampling would include the population mean. And any individual time that we do this, we don't know whether that particular interval includes the true population or not. We don't know if this particular interval is one of those 95% or not, but the confidence comes from the procedure, not the specific interval. We trust the process, in other words. To sum it all up, samples will vary, which means there is uncertainty around our sample mean. Confidence intervals help us establish a range of plausible values for the population mean. The confidence level tells us how often this process succeeds in the long run if we were to theoretically repeatedly sample over and over. The more confident we want to be about our population mean, the less precise of a claim we can make, and the wider our confidence interval will be. And vice versa, the more precise we want to be with our confidence interval, the less confidently we'll be able to claim it. Okay, so with all that in mind, how do we actually calculate a confidence interval? At a high level, every confidence interval for a mean follows the same basic structure. Our estimate, plus or minus a margin of error. Now, we've already got the estimate covered. That's just the mean of our sample, 5.8 hours. This represents the center of our interval. The margin of error is how far we're willing to go above or below our estimate, our sample mean, in order to capture the true population mean. Essentially, it's how wide of a range we're going to use. And the margin of error depends on 3 things. First is the confidence level. Remember, the more confident that we want to be, the less precise of a claim we can make, and therefore the wider the interval. Or in other words, the bigger the margin of error. Number 2, the variability of the data. The more the data varies, the larger a margin of error we're going to need. More variability means a wider interval to capture it. Less variability means a smaller interval to capture it. Number 3, sample size. The larger the sample, the more information we know about the population, so the more precise we can be in our claim. Smaller samples give us less information about the population, which means more uncertainty, and thus a wider interval. And that's all we need to know to find a confidence interval. In practice, computers can handle the computation for us. So I've put together this little Excel spreadsheet to do just that. As you can see, it has inputs for confidence level, sample size, sample standard deviation, and sample mean. If we plug those values in, the tool outputs the critical t-value, the margin of error, and the confidence interval itself. We'll save a discussion of t-value and t-distribution for another time, since primarily we'll just need to focus on the margin of error and the confidence interval itself here. But let's try it out. Using the same sample of 30 students from before, we calculated a mean of 5.8 hours. We can also compute the standard deviation of this data set too. And if we do that, we'll get 1.05. Let's use a confidence level of 95% for this problem, 0.95, and plug those values in. 0.95 for a confidence level, 30 for our sample size, 1.05 for our sample standard deviation, and 5.8 for our sample mean. This gives us a margin of error of about 0.4 hours if we round to one decimal place, and an interval of 5.4 to 6.2 hours. We can tie this back to our idea of estimate plus or minus the margin of error, because 5.8 minus 0.4 gives 5.4, and 5.8 plus 0.4 gives us 6.2. Okay, so what does all this mean? Let's back it up for a moment. The way we want to interpret this is we are 95% confident that the mean daily screen time for all college students lies between 5.4 and 6.2 hours. We can also note that if we change our confidence level, this will affect the margin of error. For instance, if we want to increase the confidence level to, say, 99%, we can see the margin of error also increases to about 0.53. All right, so confidence intervals let us take a single sample and make a careful, honest claim about a population. They don't give us complete certainty, but they do give us a process that we can trust. We take samples, compute their means, and make claims about the population mean based on our sample's size and variability. And as long as we are deliberate about specifying the level of uncertainty involved, we're making an honest, evidence-based claim about the world. Now, many other statistical ideas rely on this same foundation too, but we'll see those in some future videos. In the meantime, I hope you found this video helpful, and have a great rest of your day.